So this is work that I did with, or we're still working on this problem actually, with my colleague Bülent Yener at RPI and our student Kareem Agar, who's also the head of a big data group at GE. So Bülent does work on signal processing, and a lot of what he does involves tensor decomposition, especially tensor decompositions of skewed tensors. So tensors where you have many more samples in one mode than the other modes. So think of, say, EEG signals over time. So the question there is, we're given some huge tensor, and we'd like to find some accurate low-rank approximation to X quickly. And we want to have some guarantees on the accuracy. So this is useful for data compression, video background removal, chemometrics, hyperspectral imaging. It's just, it's like the PCA, but for multimodal data. So this is a non-convex problem. Even determining the rank of a tensor, however you define the rank, is NP hard. And the nice thing about this problem is that it's still almost linear. It's a multilinear algebra problem, so we can borrow some ideas from numerical linear algebra. Okay, so just a recap of the notation really is, so remember the outer product of three tensors. So then the tensor low rank approximation problem is to find, in this case we're looking at a three-mode tensor, I by j by k tensor. So there the problem is to find three R vectors, A, B, and C, so that A gives a good summary of what's going on in the columns of X, B gives a good summary of what's going on in the rows of X, and C gives a good summary of what's going on in the third mode fibers of X. Okay, and we want to minimize this sum of squared errors. So this particular low-rank approximation is called the canonical polyadic decomposition, or the CP decomposition. Okay, so in this talk I'm going to cover the following results. So we have a sublinearly convergent meta-algorithm, so a framework for getting algorithms for sketch CPD ALS. And we have a heuristic for adaptively selecting the sketching rate. So basically the thing that I would like to point out about this problem is that it's hard compared to sketching, say, matrix problems, but there's also room for results that you can't get in the matrix case. So in the matrix case, you have to trade off runtime for decreased accuracy. In the tensor case, it turns out that you can decrease both the runtime and increase the accuracy. Okay. So the classical iterative algorithm for finding CPD is alternating least squares, which is just a Gauss-Seidel scheme that fixes one set of your factor, or two sets of your factor matrices, and learns the next to minimize your sum of squared errors. So first you fix your old B and C and learn a better A. You fix your new A and your old C and learn a better B, and then you use your new A and B to learn a better C. So it's obvious that this has to give a sequence of low-rank approximations where the approximation error is at least non-increasing. And under some reasonable conditions, you can show that these approximations converge to a critical point of the objective. So you can't do better than a critical point in general, like finding a global optimum. Okay, so the nice thing about this problem is, like I said, each of those sub-problems is just a least squares problem. And that's because you can reshape all of those tensors into matrices. Okay? So we're going to use the first mode matricization, the second mode matricization, and the third mode matricization. So the first mode matricization you get by stacking all the columns together. The second mode you get by stacking all the rows into the columns of the matricization. And the third mode you get by taking the fibers in the third mode and make those the columns of your matricization. Okay? And now we need to reshape our outer product of these matrices A, B, and C. So it turns out that there's a nice expression for these matricizations, and it just uses a subset of the columns of the Kronecker products. Okay? So in particular, if X has L rows and R columns, and Y has P rows and R columns, then their Catriel product, or their column-wise Catriel product, has L times P rows, and it still has R columns. Okay. So this leads, like I said, to just standard matrix least squares problems, but these are much larger because we're basically using the Kronecker product, so the size blows up. Okay, but the nice thing about these problems is that they're over-constrained. So we're looking for a low-rank approximation, so our target rank R, we always take to be lower than the product of any two dimensions of our tensor. So we can see that every row of A has R unknowns, but it has to satisfy much greater than R equations. Okay, so the system is very over-constrained. That's true for A, B, and C. Okay, so then it's natural to think of using sketching. So we can sample constraints to reduce the size of the problem, or we can mix and then sample. So in the matrix setting, what happens is that the runtime will decrease because we only do one solve, and that's a smaller solve, and the accuracy isn't too affected. We know that the solution has to be less accurate than the optimal solution, but we can show that it's not going to be much less accurate. Let's just cut off. Let's see if I can. There you go. Okay, so prior work has considered sketch CPD ALS algorithms, so there's several. I picked these two representative. So the first sort of line of work is in the scientific computation community. So the latest paper that I saw there is this randomized CP tensor decomposition paper by Kolda and co-authors. So the idea there is to mix your tensor ahead of time, so just hit it with random Fourier transforms, and then that makes it incoherent, so you can sample your constraints in the usual way. And then in the TCS and machine learning community, there's a paper by Richard and his co-authors, and the idea there is instead of trying to make your tensor incoherent, you sample using the leverage scores of your system matrix at every iteration. Okay, so both of these sketch CPD ALS algorithms provide guarantees on the individual least squares problems. So basically at every iteration or every subproblem, what they guarantee is that if I exactly solved that subproblem, it would only be slightly better than my approximate solve. Okay, but this sort of guarantee is not really useful in the context of an iterative algorithm, because potentially this can allow the error to increase at each iteration, right? Because it's not comparing to the error of the previous factors, it's comparing to the error of the optimal factors. Okay. So what we wanted, also they use fixed sketching rates, and you can imagine that because this is an iterative process, as time goes on, you in fact need to modify your sketching rate, just like with SGD. Okay, so hyperparameter selection is a problem with both algorithms. And also they're vulnerable to this problem that's well known in the scientific computing community called swamping, and that's caused by ill-conditioned linear systems. So you have to be careful here because we're solving for three factors, A, B, and C. Any of them can be ill-conditioned, and if one is ill-conditioned, that can slow down the optimization process. So here's an example of swamping. So we generated a tensor where all of the factor matrices are ill-conditioned. So that means that the columns of A, B, and C are almost collinear. And then we use CPD ALS to get this blue line here. The error rate is just the relative reconstruction error of the tensor. And we just ran this for, in this case, 140 iterations. And then we compared to using proximal regularization and a very aggressive sketching rate. And you can see that even with aggressive sketching, the regularization allows us to converge in fewer iterations than regular CPD ALS. Okay, so proximal regularization helps with both of these issues. It helps to mitigate swamping, and it also allows us to get meaningful convergence results. So So what is proximal regularization? You just regularize the subproblems by requiring that when I update the factor matrices, I stay close to the previous factor matrices. So in the convex case, we know that proximal regularization doesn't change the solutions to the problem. So it turns out that in this case, even though it's non-convex, adding this proximal regularization doesn't change the set of critical points. Okay? So this is more natural than using, say, Tikhonov regularization, which is something that people also do because it regularizes your problem, but the critical points can change or do change. Okay, so as I said, proximal regularization actually does mitigate the errors introduced by sketching. And this is a good example of what I mentioned before, that in the case of these tensor problems, you can actually both decrease your error ratio and your runtime ratio. So this red dot here is if you use CPD ALS with no sketching and no regularization, and then the other dots are if you use various combinations of sketching and regularization. So we looked at Tikhonov sketching as well as Tikhonov regularization as well as proximal regularization. So in this case, you can see that if you combine proximal regularization with a pretty low sketching rate, you can still beat CPD ALS by a lot. Okay. So we're going to look at this sort of meta-algorithm for block stochastic proximal ALS, right? Or, sorry, a block stochastic proximal algorithm. So I call this a meta-algorithm because I don't say how to do the sketching. So we're going to just figure out what the sketching has to satisfy. Okay? So all we've done is we've sketched our CPD ALS steps and we've regularized them proximally. Okay, so most of the related works analyze inexact quasi-Newton methods for convex problems, or they analyze deterministic block proximal algorithms for non-convex problems. Okay? So in particular, there are deterministic analyses of this scheme. Okay, so the inexact quasi-Newton methods for convex problems that are most related to our work approximate the Hessian and or the gradient of f using sampling independently of each other. Okay? And if enough samples are used, then you can see linear or superlinear convergence. Okay? So I think Fred has work on this. Okay? And then the deterministic block proximal algorithms, they don't have randomness in the algorithm, and they assume some knowledge of the global structure of the problem in selecting these regularization constants here. And they guarantee convergence to critical points. So you can get a rate of convergence using the KL inequality, but then you don't really know what it is. Okay, so neither sets of these works apply in our case because, well, the problem is non-convex, but also the factor matrices that we get from sketching these linear systems, because the gradient and the Hessian are being sketched simultaneously, those give us bias estimates, so we can't just plug into the analysis for the deterministic algorithms. Okay, so our method of proving convergence is we argue that each sketch least squares solve actually does decrease the objective almost as much as the full least squares solve. And of course, that's subject to some assumptions on the sketching rate that we'll clarify. And then we show that this decrease can be related to the size of the gradient of the objective. So that gives us a sufficient decrease condition. And then combining that with the proximal regularization allows us to analyze this in the usual way that you do for proximal regularized algorithms. Okay? So in particular, we can show that progress is made at each step, and we get a sublinear rate of convergence to an approximate critical point. Okay, so the first step is showing that the error decreases by a fraction of the maximal possible decrease at each iteration. So the question you can ask is, what is the maximum possible decrease at each iteration? Okay, well, at each iteration, we're looking at our system matrix M, and we're asking how can we modify A to best approximate X, okay? And the modification that we're making to A is we're just adding some shift to it. So that's equivalent to asking, what shift can I add to A at time t to better approximate the residual, okay? So the best sort of reduction that I can make is to completely capture the projection of the residual onto my system matrix. Okay, so what we're able to show is that at each step, you get some fraction of that optimal reduction. Okay? And of course, the samples, the number of samples that you need, depends on your system, your residual, your regularization parameter, your failure probability, and how much of that decrease you want. Okay? Also, we assume that this regularization is smaller than the minimum singular value of m, just for technical reasons. Practically, it works well, even if it's larger than that.
That's a stringent assumption, right?
Yes, yes. So that's for the proof. Yeah. In general, you would want to, obviously.
But it just reflects what's going on in these squares problems, so from that point of view, it's good.
Mm-hmm. So I think there should be a way to get rid of it, but we've not been able to do that yet. I mean, because the goal here is just to show convergence at some rate, and we know that proximal algorithms converge, like sort of regardless of that constant, so I don't think it's super important. Okay, so the practical question is, what is this sample complexity? So it needs to be large enough, just as in sketching for matrix problems, to ensure that the geometry of the least squares problem is preserved. So in this case, that means that the angle between our residual and our system matrix has to be approximately preserved. So this is, right? So this is sort of a strange condition, right? Because you can imagine if R is, perpendicular to the range of M, then you can't get that sort of guarantee using sketching. Okay, so in order to get this sort of guarantee, you have to assume that there's a large enough fraction of your residual in the span of M. Okay, and then this is basically your usual approximate multiplication result. Yeah?
I don't want to shamelessly plug my talk, but for ordinary least squares, we are seeing exactly something very, very similar, that it matters where the spaces are.
Yeah, okay, good. All right, so the second condition is that also the range space of M must be approximately preserved under our sampling and regularization. So it's because we want this sort of inequality that we require our regularization to be on the scale of the bottom singular value of our MM transpose. Okay, otherwise this is not possible. Okay. But again, I think this is just a technical condition. We have to find a way to get rid of it. Okay, but the upshot is...
If R and P are nearly orthogonal, if you do a sort of a one-shot algorithm, that's a problem. Can you fix it up later since you're doing an iterative algorithm?
That's probably what's happening, yeah. I mean, I think that because it's iterative, it is self-correcting, but that's difficult to prove. But in general, I mean, you do expect that as you get closer to optimization, to the optimal point, that you will need to sketch better and better, like more and more, and eventually use the full system in order to continue making progress.
You can't afford to leave anything out of the
Exactly.
space. That's the thing.
Otherwise, you're going to fluctuate. Maybe you get within some, radius of your true solution or your critical point. Okay, but the upshot is that this sample complexity typically scales basically linearly in R, your target rank, and that hides some properties of the matrices and of the sampling method. So you can see that paper for the details, but it's standard sort of complexities. Okay. All right, so the result is pretty straightforward. So the idea is you can compute this delta, your change from your previous A to your next A. It's just your solution to that ridge regression, the sketch ridge regression problem. So you sketch and regularize your Hessian here, and you sketch your gradient, and then it's your gradient Hessian inverse. Okay, and now the true objective function is a quadratic function, right? It's just the Frobenius norm. So its Taylor series is exact. You just have a linear term and you have a quadratic term. And then using our assumptions, you can show that T1 and T2 are both proportional. Well, they're both proportional to the size of our optimal increase, and T1 is greater than T2, okay? So your decrease is going to be proportional to the size of your optimal decrease. Okay, so what's the consequence for the sketching rate? So as I mentioned, from the first condition, we expect that the sketching rate has to increase over time. So initially, there's going to be some small angle between your residual and your system matrix. So even if I aggressively sketch, I'm going to preserve that angle and get a lot of the possible decrease. But then when I'm near convergence, R and M are going to be nearly perpendicular. So preserving that angle requires me to be more careful with my sketching. Okay, so I point this out just because that suggests that previous sort of analyses that use fixed sketching rates might fail in the long run, okay, if you run for long enough. Okay, so next we can relate that guaranteed decrease to the size of the gradient of the objective. And okay, so we know the gradient of the objective is just the gradient times the system matrix, right? I mean the residual times the system matrix. So we can plug in a projection onto the range of the system matrix. And remember, we can control the size of our decrease in terms of this matrix, the residual projected onto the system matrix. Okay, and then we assume that our factor matrices, so in this case, B and C are bounded. So that means that we can actually get a lower bound on the size of the optimal decrease in terms of the size of the gradient of the objective, because this thing here is bounded. Okay? So that means that we can say, in fact, that the decrease we observe is some fraction of the size of the gradient squared. So this is called the sufficient decrease condition. And then just using standard results, when you have sufficient decrease, if you make just a few more assumptions, so namely that your gradients are Bloch-Lipschitz in your factor matrices with some constant that's bounded along the solution path. So that's a strong assumption, I know, but it's a standard assumption in the deterministic analysis as well. So under that assumption, we know that sufficient decrease is achieved from before, right? So we have these two assumptions. And then we further need to know that this is the sort of fraction of the optimal decrease at every step that we achieve, that's CT. So it's between 0 and 1, and lambda is our regularization parameter. So this is 1 over CT plus 1 over lambda. As long as that thing is uniformly bounded along the solution path, so that means you need to choose these things as you go along so that they're uniformly bounded, then we get what we want. So we get a rate of convergence to an approximate critical point, so a point where the gradient is small at a rate of 1 over square root of t. Okay? Yes?
So you said in your application the tensor is really skewed, right? One dimension is much bigger than the other.
Yeah.
So your algorithm treats all the same, right?
So we're sampling columns of x, and the way that we sample columns, instead of uniformly sampling them, we sort of skew the sampling probabilities to avoid sort of oversampling the skewed portion.
Oh, I see. Okay, thank you.
Okay, so that's a meta-algorithm because we didn't say how to sample. We just said as long as the way that we sample satisfies these things, then we get some guaranteed convergence rate. So to get a concrete algorithm, we have to do two things, right? We have to choose how to get our regularization parameters, and we have to say at every iteration how much to sketch and how to sketch. Okay? I'm just going to go ahead and assume that we have a good regularization parameter because I don't know how to do that yet. Okay? In practice, we find that like 1 times 10 to the minus 3 works well. Okay? So we just fix that in all of our experiments. And then prior work, so the two works that I mentioned, as I said, Richard's work has used the leverage scores of our system matrix and a fixed sketching rate. And the Kolda et al. Work says just randomly rotate your tensor so that it's incoherent and do column samples at some fixed sketching rate, okay? But I want to know, can we do better than that? Is there some better way of choosing our sketching rate? Okay, so the key observation is that this low rank approximation is an iterative process. So like I said, as in SGD, when we get closer to convergence, we expect that we need to sample more constraints. So how do we do that? Well, we just think that the performance of a given sketching rate historically should be predictive of its future performance. Okay? So that suggests that we can use some online learning approach to sort of figure out which sketching rates perform best and then use those. Okay? So this allows the user to specify a range of sketching rates. So rather than have to magically choose the best sketching rate, they can just select n sketching rates that they think will work well over the course of the optimization, and then over the course of the optimization, we will sort of track the optimal choice. Okay, so to do that, we use a label-efficient multiplicative weight update algorithm. So the idea is, remember, the point of sketching is to trade off the decrease in the error with a decrease in the runtime. Okay, so we choose our loss to reflect that. Our loss is going to be large and negative if, when we use that particular sketching rate at time t, the approximation error went down by a lot and the runtime wasn't too bad. Okay? So once we know the loss of all of our arms, we can update our probability distribution that says how to sample from our arms, so that the arms where we had a large negative loss increase in probability. Okay? But that's expensive because that requires doing n different solves. So instead, that's where we do this label efficient updating scheme. So at every iteration with some probability, we choose to update all of the weights. Otherwise, we don't update any of the weights. Okay? And then at every iteration, we use the sketching rate that's selected, according to these probability distributions to compute all three of our factors. Okay? So this parameter epsilon determines our update frequency. And typically, we were taking epsilon to scale like 1 over the number of arms so that we amortize the cost of computing these losses. Okay? And eta here determines the aggressiveness of our weight updates. And then we also suggest to take one arm to be the fully constrained CPD ALS, so just take a full ALS step, because that ensures that convergence is possible. And then usual arguments for multiplicative weight update algorithms give a regret guarantee. Okay, so this is a starred regret guarantee because we have to assume that at every iteration, the error is actually going down. So how do you do that? Well, you have to check the error of this iteration and the previous iteration and say we're not going to change the factor matrix if the error didn't go down. So in practice, you don't want to do that. Okay, so this doesn't really apply to what you do in practice, but think of it as a moral result. Okay, so what does this say?
Is this, and that's fair, is this star notion yours, or was that in the area prior to this?
Oh, no, I
mean, other people have done the same thing.
No. And so I would like to be able to say that you don't need to check that the loss is going down, but like the standard proofs for this assumes that that loss will be going down.
But you need that because of the sketching.
Yeah, the sketching is what makes. So basically, the problem with sketching is that the expected error is biased, so you can't really say you can say with high probability that it goes down, but I don't know what happens to the expectation. Okay, but what is this saying? Well, it's saying that we track the performance of the best arm. So here I'm assuming one of the arms corresponds to fully solving the ALS system. So this would be the performance of that arm. After t iterations, this is the error of that arm. And we see that we're only 1 over square root of t, basically larger than that error. Okay. Okay. So is that time?
Still 10 minutes.
Okay. All right, so we'll just cover some numerical investigation of that algorithm. So like I said, that theory is a little pessimistic because it says, okay, I need to guard But in practice, this has a better time accuracy trade-off than if I don't use sketching. Okay, so here we're looking at this blue line here. Paraslice is just a parallel implementation of CPD ALS. And then we're just looking at the effect of using this multiplicative weights update algorithm with different numbers of arms. Okay, because the more arms it can handle, the more freedom that gives the user in not needing to be careful with selecting their sketching rates and letting the algorithm adapt to it. Okay, so you can see when you use 5 arms, so here we're looking at a order of magnitude of 100 difference in the arms. You can see here if you use 5 arms that you do a very good job of converging compared to just unsketched ALS. And you can even go up to 100 arms and still do a good job. Okay. And again, this is on an ill-conditioned synthetic tensor. And we're looking for a rank 50 approximation. Okay.
Why do you think it gets flat like that? Why do you think it gets flat like that and then tips in both of those?
So that's sort of based on how frequently you're letting it update the sampling probabilities.
So for a while it was sort of like sampling too aggressively, not making progress. Then you updated the arm.
Well,
Or then you sample more aggressively.
so what happens is the more arms you have,
Yeah,
the less often you update your probabilities.
I see. Okay.
So that's why you see it changing faster over here. It's sort of tracking the rate faster.
So with that ill-conditioned tensor, you're not entitled to more than 2 digits, 10 to the minus 2 relative error?
I don't know. So that's a good question. The problem is these are, what do you call them? They're randomized algorithms, so what is the stopping condition, right? We actually spent a lot of effort trying to find good stopping conditions, but it's hard. So we just ran for a fixed, like 10
You made it hard
10
on
minutes.
yourself, right? You started with an ill-conditioned problem.
Yeah, exactly, because we wanted to see the effect. This is a hard problem. We wanted to see the effect there. Okay, so then you could also ask, well, what if I just randomly choose the arm, right? If that works better than trying to track the best arm, why not do that? So here again, we're comparing to this blue line here is CPD ALS. Okay, again, this is on an ill-conditioned tensor, so you see it's converging slower. And the green line here is where we're just randomly picking one of the sketching rates. Okay? And this blue line here is where we are, this blue line here, is where we're using the multiplicative weight updates to sample our columns. Okay? So we see that it does beat randomly choosing our sketching rates. So here's an example application. So I mentioned one of the uses of tensor decomposition is hyperspectral imaging. So this is a data set called SAMSON. It's a standard hyperspectral imaging data set. So here's the original frame. Here's the frame reconstructed from our decomposition using just ALS and reconstructed using our algorithm, our multiplicative weights update algorithm. So they are effectively identical, but this decomposition took approximately a third of the time of the ALS decomposition, and that's significant, right? So in scientific computing, I think that's a significant gain. Okay, here's an example from this was a background subtraction data set. It's it's a video of a guy sitting on a bench in the park, and the idea is that basically he's static and some of the stuff in the background static as well. So when you do your tensor decomposition, it will subtract out the static stuff, right? That will fall in your top, your top factors. Okay, so here's the original still. Here's the reconstruction from ALS. Here's the reconstruction from multiplicative weight updates. And just on the same scale, here is the difference between those two images. So you see that there's no perceptual difference, but again, the multiplicative weights update algorithm took 30% less time than the full algorithm. Okay, and you can look at the error, the standard deviation of the error, the time, and the standard deviation of the time. And so to within one standard deviation, the multiplicative weight updates algorithm beats both ALS. So again, this is a parallel implementation of ALS. And this is ALS with a fixed sketching rate. So the optimal fixed sketching rate, because we wanted to see, remember these sort of prior to this stuff, you were using one fixed sketching rate. So how would you choose that? Well, okay, you can cheat, run for a whole bunch of sketching rates and pick the one that gives you the best error. So that's what this line corresponds to doing, okay? And you can see that tracking the sketching rates outperforms both in terms of time and error to within a standard deviation. But also notice that the time, the deviation in the error and the time goes up, okay, as you sketch. So if you use one sketching rate, a fixed sketching rate, yes, your deviation increases over not sketching. And if you use the multiplicative weights, your deviation goes up again, right? But it's still better to within one standard deviation. Okay, so in conclusion, we showed that a sketch proximally regularized ALS scheme has this sufficient decrease property, and therefore it converges sublinearly. And we introduced a particular way of selecting this sketching rate to sort of help ameliorate that problem of hyperparameter selection. But the overall idea here is that regularization and sketching rate adaptation are just useful ideas, so it would be good to see that space explored more, both for low-rank approximation and for other tensor optimization problems.
So for the ALS, right?
Yeah.
Instead of fixing 2 of the 3 and optimizing over 1, you could have fixed 1 and optimized over 2 by solving an eigenvalue or singular value problem. Is that worse? Is that known to be worse?
So yeah, that's just a nonlinear least squares solver. I think this is one of those things where it depends on the scale of the data, like what's the best algorithm.
Randomized solution of an eigenvalue problem is much harder than a randomized least square solution.
Yeah, but you presumably get more because you've optimized 2 dimensions. I don't know. That's a
I
comparison.
think
That's a
it
trade-off.
all depends what you want from the eigenvalue problem. If you just want a subspace, that's okay. But if you also want values, that's really not as easy.
You don't want diagonal. You just want some solution to the eigenvalue problem.
So I think, again, this depends on the scale of the data and how much effort you're willing to put into it. So you could also use just gradient-based methods, but I think this is a sweet spot between sort of the full nonlinear least squares problem and gradient-based methods. This is what people have sort of converged on in the scientific community. Sorry, scientific computing community.
Did you also try
David?
using tensor sketch?
Tensor sketch, do you mean for power iterations? Or?
I mean, like
Oh, count sketch?
like the tensor version of count sketch instead of these other 2 methods you mentioned, the leverage core sampling.
Well, I don't, how would I apply tensor sketch to my matrix? I could see how to apply it to the low rank factors, but to the matrix itself.
I mean, when you're solving the regression, you have a product per product regression, right?
I mean, we took our tensor and matricized it.
And it has a special form, so it can be sketched quickly with.
No, the matricized version of the input data doesn't have a special form. The low rank factorization has a special form. But certainly, so I would say you could use like count sketch. All of the sort of standard sketching methods will work here. I'm aware, do you have the paper with
But isn't the
N
matrix
increment?
version of the Kronecker product came from a Kronecker product?
The matricized version?
But your least squares, like your big wide matrix is a.
No, not the matricization of the input.
Not the input part, but the.
Yeah, the other part.
Assuming the input is sparse and.
Oh, sure, yeah, okay, yeah, if you want to, but this is not, we're not in that setting. This is like a full dense tensor.
But I thought the nice part of your result was it was oblivious of your result held for.
Yeah,
all
it's
sketching.
oblivious of the type of sketching. So you could go ahead, if it is sparse, yes, you can go ahead and use a
But I mean,
tensor.
even for dense matrices, like the time could be would still be comparable to, say,
Gaussian.
well,
I
I
don't
mean, it would
think
be
it's-
faster than that, but comparable to like subsample randomized atomized.
Oh, sure, yeah, but I'm not suggesting, so the reason that we're doing this is because these are very large tensors and we just want to use column sampling. But yeah, certainly the theory will hold for any sort of sketching method, and it'll be stronger for those ones that do the mixing and sampling. Yeah. But I think the time dependence may get a lot worse.
Why are you describing it in terms of tensors? Because the setup you have should work for any of a range of other people, non-convex optimization that's not arbitrary, but is structured.
Sure.
We'll do some iterative alternative least.
Uh,
Do you need to be very rectangular, or would it hold for those two?
Well, it's because I used the fact that our objective is exactly quadratic, but you could imagine, approximating your general function with a quadratic and iterating. Yeah. I mean, you could also imagine regularizing with Bregman divergence instead of, so those are all sort of things that we're thinking about.